And hello, this is Mr. Weston. I'm recording this video for SPH4U, my grade 12 physics class. And what I wanted to do is explain some of the centripetal force problems, because the way you do it, the way you set up your free body diagram is a little different than what we've done before. So let's jump right into it and look at question number 1. We have a 1,000 kilogram car, drives around a circular track with a 20-meter radius. If the coefficient of friction is 1.07, what is the car's maximum speed? Now, if you imagine a car driving on the road, obviously you need friction between the tires and the road in order for the car to maintain its position on the road. If the car is, loses friction and is trying to go around a curve, it's just going to slide off the road into the ditch. You need friction to speed up, slow down, and also to turn a corner. So here we've got the radius of the curve, we've got the coefficient of friction, and we want to know the maximum speed that the car can go around this curve. Now you can imagine, again, a car going too fast, even with friction between the tires, it's eventually going to slide if it goes too quickly. So the first thing we want to do is set up our free body diagram. The free body diagram we're going to draw, if we try to look down from above, we're not going to see the gravity force and the normal force, but we'll see the curve of the road. If we look at the side of the car, we'll see the gravity force and the normal force, but we won't see the direction that we actually want, because when an object is traveling around in a circle, so here we have a car traveling around a circular track, if you're sitting in the driver's seat of the car and you point towards the center of the circle, well, you're going to be pointing sideways, because with centripetal acceleration, the direction of the acceleration is always towards the center of the circle. So what we want to do is draw our free body diagram like this, where we can see kind of the front of the car. We've got a normal force up, gravity force down, and friction force to the side. Now there would also be some, forward and backwards, but we're assuming the car is traveling at a constant speed, so all that's going to balance out, so we'll just ignore that for now. And the only thing causing the car to accelerate sideways, to accelerate with a centripetal acceleration, is that friction force. Gravity and normal force are vertical. Friction is the only horizontal force. There's no cables or ropes or anything else pushing on the car. So that's pretty much it. So we know the gravity force. It's 1,000 kilograms, so 1,000 times 9.8 is 9,800 newtons. The normal force will balance that, also 9,800 newtons. And so we can figure out the friction force because FF equals mu Fn. So we substitute in the 1.07, our coefficient of friction, multiplied by the normal force, and we get 10,486 newtons for our friction force. Now, question, is this static friction or kinetic friction? Well, the car is moving, but technically the tires are not sliding across the road. The tires are gripping the road, and as the wheel turns, as the car moves across the road, it is always maintaining that static friction. It is not sliding. So this would be a static coefficient. Although there's only one given in the question, so that's the one we're using. Doesn't really matter. Since that force is the only horizontal force, the centripetal force has to be less than or equal to this value. If we need a centripetal force bigger than that, well, that's all we've got. We've got a friction force. We don't have any more. So if we try to go too fast and we need a force bigger than that, friction can't provide it. The car's going to slide and end up in the ditch again. So if we set our centripetal force equal to that value, that gives us the maximum possible speed that the car can have, and still friction would be able to obtain or apply that amount of force to get it to travel around that at that speed. So our centripetal force is mv squared over r. Our centripetal force is equal to the friction force. We set that equal to 1,000 v squared over 20. 20 is our radius. Solve for v, and we get 14.5 meters per second, or approximately 52 kilometers per hour. And don't forget, we need a little therefore statement at the end. Okay, if the track was covered in ice with a coefficient of friction of 0.005, what would be the car's maximum speed? Now, this is something that occurs obviously in real life. Living in Hamilton, Ontario, every winter, the first time it snows, everybody forgets, oh yeah, I need to slow down when there's ice and snow on the road, because that does impact the coefficient of friction, right? The road becomes more slippery, there is less friction, and therefore it takes more time to stop. It's more difficult to travel around curves because you just don't have as much friction as you would, say, in the summertime. So 0.005 is a very, very small coefficient. This would be like if you're in the middle of a hockey arena, trying to drive, there would be very little friction. However, let's move ahead with that. So we've got our friction force is the coefficient times the normal force. Our free body diagram is the same as previously. All we're changing is the coefficient, so we end up with a much smaller friction force, in this case only 49 newtons. So if we apply that to Fc equals mv squared over r, our centripetal force is mass times centripetal acceleration. We have 49 equals 1000 v squared over 20, and solving again for v, we get 0.99. So we get a much smaller maximum speed, roughly 3.6 kilometers per hour versus 52 kilometers per hour in the previous example. And again, the reason is there just isn't as much friction. Okay, for our next example, a 1,000 kilogram car drives around a frictionless track with a 20-meter radius. The track is banked 20 degrees to the horizontal. How fast must the car travel to maintain its position on the track? Now, at first glance, this question is kind of weird. We have a car traveling around a curve, a 20-meter radius, and the road is frictionless. So how can that be? Well, the car typically is going to require friction in order to maintain its position on the road. It's going to slide if there is no friction. In this case, however, because the track is banked to the horizontal, we can imagine that if the car is stopped, it's going to slide towards the middle. It's going to slide down the slope if the car is not moving. If the car is going around this curve too quickly, though, it's actually going to slide up the ramp and end up going over the top or sliding into the ditch or whatever's on the other side. If the car travels around this banked curve at just the right speed, it can actually maintain its position where it's basically sliding around the inside of this curve, like going around the inside of a bowl, you can imagine. As it travels around that curve at just the right speed, it will not require any friction to maintain its position. But that only happens at one specific speed. A little bit too slow, it's going to spiral down towards the middle. A little bit too fast, and it's going to spiral up towards the top and again fly off the edge. So what is that speed? Well, we're going to draw our free body diagram similar to before. Looking from the front, we have a gravity force pulling down. Obviously, gravity pulls things down. The normal force, again, our rule is the normal force has to be perpendicular to the surface. It's not necessarily up. And in this case, because our ground is at a slope, our normal force is going to be on a slope. It's going to be angled 20 degrees to the vertical because our slope is 20 degrees to the horizontal, right? Normally the normal force would be up. As you angle the ground, whatever angle the ground tips up, the normal force will tip sideways from the vertical that amount. Now, before we start doing our F net equals ma, what we want to consider is the direction that the car is actually accelerating. Because the car is accelerating towards the center of the circle, but because our ground is sloped, it kind of confuses things a little bit. Normally, when we're doing a question like this, where we've got gravity down, normal force perpendicular, friction force parallel to the slope. This question doesn't have friction, but we will get into some that do have it. Typically, what you want to do is kind of look at the perpendicular and parallel because the normal and friction force you don't know, and by doing that, you can kind of eliminate one when you do your component vectors. The problem is with these centripetal acceleration problems is the car is accelerating horizontally. It's accelerating towards the center of the circle. So if you look down from the top, the acceleration is towards the middle of the circle as it goes all the way around the curve. However, as we look from the front, vertically, we don't want it sliding up. We don't want it sliding down. We don't want any vertical acceleration. So we can't use perpendicular and parallel because that would actually make our lives more difficult. Technically, you could do it, but then you'd have components of your acceleration in both. Whereas if you use vertical and horizontal, then we can say vertical is zero acceleration and horizontal is all of our acceleration, which again it complicates our normal force and friction force by doing vertical and horizontal, but it makes the acceleration a lot easier, and that's the one we're really looking for here. So looking at this car from the vertical direction, F net equals ma, we have gravity force that is vertical. So we have all of it. All the gravity force is down. The normal force is up, but it's on an angle, so we have some of the normal force. Fn cos 20, because again, it's angled 20 degrees from the vertical, equals mass times acceleration. Well, in the vertical direction, there is zero acceleration. Okay, now the A that I put on the diagram, that is not a force. That is just indicating the direction of the acceleration. The only forces we have are gravity, normal force. That's it. There's no friction in this question. There's no cables or ropes attached to it. Those two are it. So now that we've got our F net equals ma, we can say 9800 is our gravity force, equals Fn cos 20, and solve for our normal force, which is 10,429. Our normal force is actually bigger than the gravity force because it's traveling around that sloped curve. Okay, once we've got our normal force, now we can look at the horizontal case. In the horizontal, there is F net equals ma. Our gravity force disappears because all of it is vertical. None of it is horizontal. So in the horizontal direction, it's 0 for gravity. The normal force is Fn sine 20. Again, in the vertical case, we had Fn cos 20. So now for horizontal, it's sine. Whatever you use in one, you're going to use the opposite one for the other component. Equals mass times acceleration. Now in the horizontal, we do have an acceleration. So we have to go 1,000 times a. And because we know Fn, we know sine 20, we can solve for a, which is 3.567 meters per second squared. Since that acceleration is our centripetal acceleration, AC equals v squared over r. Sub in our AC, sub in our radius, solve for v, we get 8.4 meters per second as our speed. Now, another way we could have done this is rather than solving for a, we could have said Fn sine 20 just equals our centripetal force. Technically, the net force is a centripetal force, right? And vice versa. If something is traveling with the centripetal acceleration, acceleration and net force go together. That's Newton's second law, F net equals ma. So if you have a centripetal force, it also has a centripetal acceleration, so you can just put Fc straight into your F net equals ma, right? Where the centripetal force is mv squared over r. M is your mass, v squared over r is your centripetal acceleration, so it's really just the same thing, right? Mass times acceleration, m times v squared over r. You can do it in 2 steps, or you can do it in 1 step. Either way, whichever one makes more sense to you. And don't forget your therefore statement. The car must travel 8.4 meters per second to maintain its position on the track. Okay, so last question. A 1,000 kilogram car travels around a 30 meter radius track. The track is banked 30 degrees to the horizontal and has a coefficient of friction of 0.40. A, what is the maximum speed the car can travel without sliding up the ramp? B, what is the minimum speed the car can travel without sliding down the ramp? Okay, so this question is similar to the one we just did. We have a car traveling around a curve with a radius. The curve is banked to the horizontal, and the difference is this time we have friction. So friction allows the car to go a little bit off of that perfect ideal speed that would allow it to travel around the curve, right? When engineers design roads, what they want to imagine is a car traveling around this road, and let's say it's an on-ramp to a highway. And let's say the car is traveling at a normal speed, and then all of a sudden a winter storm hits and you get black ice. Well, all the cars are going to start sliding off the road. By banking the curve, what it allows them to do is alter the speed in such a way that if the car is going a little too fast or a little too slow, it can still safely navigate that curve. So in this case, we've got a coefficient of friction, 0.4. This is a little bit less than what it would normally be for a car. Car tires on asphalt, it's going to be around, 1.1, 1.2, somewhere in that range. So here we've got a road that is abnormally slippery, and as the car navigates this curve with this coefficient of friction, if it's going a little bit faster than this banked curve would normally allow, the friction will keep the car in place, prevent it from sliding. Similarly, if the car is going a little bit too slow, friction will intervene and prevent it from sliding, and again keep it on the track. But there's a limit, right? If there was no friction and this car was stopped, it would slide down the ramp. Because there is friction, this amount of friction in this case is not enough to prevent it from sliding. It would slide down. But if it's traveling around the curve with a velocity, that will also factor in, and so it will maintain its position. Okay, so let's jump into it and see how that affects it. First, we need our free body diagram. Again, we're drawing from the front. We've got a gravity force down, normal force perpendicular, and we've got a friction force that is parallel. So for question A, we're looking, what is the maximum speed the car can travel? So if the car is going too fast, what's it trying to do? It's trying to slide up that ramp. And so what's friction going to do? Friction is going to prevent it from sliding. It's going to act down the slope. Now the rule is friction is always parallel to the slope. Normal force is perpendicular, so we've got those. But it is specifically down the slope for the friction force. Okay? Because our acceleration is still horizontal, we still want to make sure that we're looking in the vertical and horizontal case. Again, if we try to do perpendicular and parallel, because I don't know the normal force yet, I don't know the friction force yet, if I try to eliminate one by doing perpendicular and parallel, I'm going to have a component of our acceleration in there that I don't want. Okay, so I'm going to keep it with vertical and horizontal. In the vertical direction, F net equals ma. In the vertical direction, I have gravity, all of it. I've got a friction force, some of it, and in this case, it's FF sine of 30. So if the road was flat, friction would be horizontal. By angling the ground up 30 degrees, I'm angling the friction force down 30 degrees. So that 30 degrees is from the horizontal. So my vertical component will be sine. The normal force is Fn cos 30 because, again, that 30 degrees is from the vertical. So my vertical component will be cos. And I'm making it negative because it's up. The gravity force and friction force are both technically down if I'm only looking at the vertical components. The normal force component, however, is up, so it's going to be negative. And of course, that whole thing equals 0 because there is no vertical acceleration. It's all horizontal, as I said already. Sub in what we know the gravity force is 9,800 newtons because it's a 1,000 kilogram car times 9.8. We know that the friction force is equal to the coefficient times the normal force. FF equals mu Fn. So we can replace FF with 0.4 times Fn, and the sine 30 is still there. And now we've only got one unknown. We've only got Fn as our unknown variable in this equation, and so we can solve. We can factor out our Fn. Fn times 0.4 sine 30 minus cos 30 equals, if I bring the 9,800 to the other side, it equals negative 9,800. And so we're going to have a negative sign on both sides, giving us a positive final answer, where Fn equals 14,715 newtons of force. Switching to the horizontal, in the horizontal component direction, the Fn equals ma. So in the horizontal direction, we've got a component of our friction force, Ff cos 30, plus Fn sine 30. So whatever components we had in the previous direction, in the vertical direction, we've now got the rest. So gravity, all of it was used, now we have none. Some of our friction force was used, we used sine, so now we've got cos. Some of our normal force was used, we had cos, now we've got sine. So Fn sine 30 equals ma. Sub in our values, again, replacing the friction force with 0.4 times the normal force. I know the normal force, so we can actually put numbers right in. 0.4 times the normal force of 14,715 times the cos of 30 degrees plus, again, our horizontal component of our normal force equals 1,000 v squared over r. Do a little bit of math, solve for v, and we get 19.3 meters per second as our maximum speed. Okay, so the friction force, because it depends on the normal force, the friction force will apply up to a certain amount. In this case, it would be 0.4 times the 14,750 newtons. Anything less than that, friction will prevent it from sliding. As soon as you exceed that, the car is going to slide because the friction force can't keep up. That is the maximum amount that the friction can apply. So we end up with a maximum speed of 19.3, where as soon as we try to go 20 meters per second, those tires are going to slide, and it's going to slide up the ramp and off the curb. Especially because kinetic friction is usually less than static. So as soon as you lose that static friction, it's going to slide quite a bit. So the car's maximum speed is 19.3. Don't forget your therefore statement. Any faster and it will slide up. For part B, we have to modify our free body diagram a little bit. So we've still got a gravity force, 9,800 newtons down. We've still got a normal force, perpendicular to the slope. Our friction force, however, we're going to switch it because now we're looking for the minimum speed. What is the car trying to do? Well, if it's going too slow, it's trying to slide down into the middle. So the friction is going to oppose that and be parallel but up the slope. So in the vertical direction, because again, our acceleration is still horizontal, so we're going to stick with our vertical direction. F net equals ma, gravity force minus the friction force component, because again, it's up instead of down, so now this becomes negative. This is really the difference between this question and the previous one, the direction of this friction force. Minus Fn cos 30 equals 0, 0 vertical acceleration. So when we sub in our numbers, we solve for the normal force of 9,193 newtons. Okay, so because we're traveling around a banked curve, because we're dealing with a centripetal acceleration, the normal force actually changes depending on the speed of the car. It was larger in the previous example. Because it's going slower, that normal force decreases and changes the friction force and everything else. Gravity stays the same, but the normal force and friction force, because now they're working together to oppose gravity, the normal force doesn't have to work as hard. Okay, so we've got our new normal force. We can solve for the horizontal, F net equals ma. We have our, in the horizontal direction, our normal force component towards the center of the circle. Gravity is 0, it's not horizontal. Our friction force, however, is now the other way. Again, in the previous example, normal force and friction force were both to the right. So they work together to provide that centripetal acceleration. They were both in the same direction. Here they're opposing each other. The normal force is to the right, the friction force is to the left. So we've got Fn sine 30 to the right minus Ff cos 30, because it's to the left, equals our centripetal acceleration, mv squared over r. When we sub in our value for the normal force and our value for the friction force, because friction force is 0.4 times the normal force, we can sub in our mass, sub in our radius, we get a v of 6.5 meters per second. Now that is our minimum speed. Again, the friction force up the slope, the maximum that friction force can be, still requires the car to have a speed of 6.5 meters per second. If it's going any slower, friction force is not enough to prevent it from sliding into the middle. Okay, so we can do our therefore statement. The car's minimum speed is 6.5. Any slower and it will slide down the slope. Okay, I will be posting these notes along with your homework for this week. I hope you're doing well and staying safe. And send me your questions via email. Make sure you're staying on top of it. Pace yourself. Do a little bit every day. And I'll talk to you again soon. Okay, bye-bye.